Hello all. Today we are going over a Unit 3 paper and specifically Unit 3A. Okay, and these A versions are backup papers that Edexcel uses, is my understanding and is what people have been telling me in the comments. Anyway, this one is from October 2025, so it's quite recent. There are not a lot of Unit 3 past papers in my channel yet, so I think it's going to be the fourth one. So I hope it's useful to people. Let me say one more thing before we dive in. So you have 80 minutes to complete this paper, and I think it awards 50 marks, maybe. Is that so? Let me check. 50, yeah. So you have about 2 minutes, maybe a minute and a half per mark, meaning that if a problem awards 10 marks, it should take you about 15 minutes. So try to stay on time. And as usual, read the problems carefully before you answer. Half the answer is in the question, is what I say. And let's dive in. The first question is not the most imaginative question in the history of physics, but let's do it. A group of students are given a packet of 500 sheets of paper and asked to determine the thickness of one sheet of paper. Okay, question A, the students use a digital caliper to measure the height. Question I, which awards 4 marks, so you have to provide a detailed answer, okay? Describe a method to accurately determine the thickness of one sheet of paper. So let's go to a clean page and let's start writing a few arguments. So first of all, a single sheet is too thin to measure directly. So, comma, okay. So the trick is to measure multiple papers, and divide. Okay, so that's the first thing you can write. Before starting, okay, check the caliper reads 0 when fully closed. Okay, that's the other thing. And correct if not, okay, of course, and correct if not, okay. Close the jaws onto the stack gently, okay. Squeezing too hard on the calipers, I mean, so squeezing too hard gives a false reading. Okay, so that's the other thing. The fourth thing is to make sure the sheets are neatly aligned, okay, with no gaps between them, okay. Otherwise, you will be measuring air. I mean, the air gap between sheets, so they have to be closely packed, pretty much. Okay, so measure the height of all 500 sheets together. Let me use a new line. This is a 500, by the way. It looks funny. So, okay, of all 500 sheets together and divide by 500, okay, to get the thickness of one, pretty much, okay. Take the measurement, okay, at a few different points, points on the stack, okay, and average the results, okay, since the stack might not be uniform. Okay, I think this is longer than I intended, but I hope it's it's a full answer that will give you full marks. Okay, so let's go to question 2. The students measure the height as 60 millimeters. Determine the percentage uncertainty in the measurement of the height. Okay, so let's create another clean page. So this is 1A part 2. Okay, so the absolute uncertainty for calibers is the smallest deviation of the caliber is 0.01 millimeters. Okay, this is something you should know. Okay, over 2. Okay, so the absolute uncertainty is 0.05 millimeters. Now the percentage uncertainty is equal to the absolute uncertainty over in the thickness. Okay, over the thickness. Sorry, it's a little bit cryptic. Let me rewrite it. So the percentage uncertainty in the height, okay, or the thickness, I'm sorry, is equal to the absolute uncertainty in the thickness over the thickness times 100. So 0.05, excuse me, over 60 times 100 yields something really tiny, 8.33 times 10 to the negative 3%. So that's 0 pretty much, but okay, that's the answer. The students were then asked to determine the density of the paper and took the following additional measurements of the packet of paper. So they took four measurements of the width and the length. Okay. Question I, determine the mean values of width and length. Okay. So let's do this here. So BI. Okay, so for the width, we have to add all those values. 210.2 plus 210.35 plus 210.15 plus 210.25 over 4. Okay, so 210.24 millimeters. And then the length is 297.25 plus 297 plus 296.75 plus 297.10, okay, over 4. Okay, so this yields 297.03 millimeters. Okay, I think there are no more questions. Yeah, there is part 2. The students measured the mass of the packet of paper with a balance as 2.07 kilograms. Determine the density of the paper in grams per cubic centimeter. Okay, so there is also part 3, as you just saw. Okay, let's do part 2 of question B. Okay, so density is mass per volume. So we have 2.07 kilograms, but 1 kilogram is 1,000 grams. Okay, and then for the volume, we will use centimeters. So 210.24, which is the width, will turn into 21.024 times 297.03, this is millimeters, by the way, will become 29.703. And then we also have 60 millimeters as the thickness, so that's 6. And then everything is centimeters cubed. Okay, and this yields 0.55 grams per cubic centimeter. Okay, so that's the answer. Let me check really quick. I have the mark scheme that I never check really. Okay, but let me make sure that we found the right answer. Yeah, it looks good. Okay, now part 3, identify a potential source of systematic error in the measurement of the mass. Okay, if the balance, okay, that's one source of error. So if the balance, actually, let me go back here and create another clean page. It's gonna be prettier. Okay, so B and then part 3. right? Okay, so if the balance was not zeroed, okay, so that's, it will have a zero error, in other words. Every reading, okay, will be shifted by the same amount. Okay, so this will be a systematic error, okay, because it affects every measurement by the same amount. Okay, so this was question one. Again, kind of a boring question for a physics question, but okay, we have to work with what they give us. Okay, so let's move on to the next question. Okay, question two. A student investigated the interference of sound waves. The student used a signal generator with two loudspeakers as shown. Okay, so you see that the signal generator provides signals to the two loudspeakers. Okay, question A. The student adjusted the signal generator output until he heard the loud continuous sound from the loudspeakers. State the reason for connecting both loudspeakers to the same signal generator. Okay, let's use a clean page. So this is 2 part A, part 1. So students, or is it, I think it was a student. Anyway, so students need to emit sound waves, okay, with a constant phase relationship, okay, to each other, okay. If they were driven by two separate generators, so if they were driven by two separate generators, okay, the phase difference between them would drift randomly, okay, and the interference pattern would not stay still. So the interference pattern would not stay still. So yeah, I think that's a good enough answer. Okay, let's move on to part two. Identify a health and safety issue for the student and how it may be dealt with. Okay, so part two. So a loud continuous sound is not a good thing, I guess. So loud continuous sounds from the speakers, okay, can damage hearing. Okay, let me try to write better letters. Damage hearing over time. So you can use ear deafeners or defenders. Okay, reducing the volume. So let's write or, okay, or reducing the volume, or staying farther away from the speakers. Okay. So yeah, I mean, limit or limiting exposure time to the sound. Okay, so that's the answer. Okay, let's turn the page. Part B. The student walked along a line between points A and B, okay, carrying a sound meter. The sound meter indicated the positions of maximum sound intensity as shown. Okay, so we have the key there, position of maximum sound intensity. So these points, okay, have maximum intensity. Okay, the student measures the distance of each maximum from point A using a tape measure. Determine part I. Determine, let me see, an accurate value for the separation W of the maxima. Okay. Part I, determine an accurate value for the separation W of the maxima. So we can subtract pretty much this value from this value and divide by how many maxima there are. So by how many distances, I'm sorry. So 1, 2, 3, 4, 5, pretty much. Okay, so let's do that. Let's turn the page. So this is part B, part I. So W is 3.33 minus 0.22 over 5. So 0.62 meters is the answer, which kind of matches this distance 1. Okay, close. So part 2, I mean, from 0.22 meters to 0.85 meters, it's almost 0.62 meters, kind of. Okay, it's actually 0.63, but okay. All right, part 2. The relationship between W and the wavelength lambda of the sound waves is given by W equals to lambda times capital D over S, where D is the perpendicular distance between the loudspeakers and the line AB. So this is D, I guess. Okay, yes. And S is the separation of the loudspeakers. So that's S. Okay. This is kind of crowded, so maybe, okay. So this is S, and this is D. Okay. Determine the value of lambda. They give us D and S. Okay, so this part 2. W is lambda D over S, but we want to find lambda, which is W times S over D. So that's 0.62 times 1.1 over 4, which is 0.17 meters. Okay, so no more questions here. Let's turn the page. Part C. The student used this investigation to determine the speed of sound in air. Question I, to determine an accurate value for the speed of sound, the student would need to use other apparatus. Explain what other apparatus the student would need. So I'm going to use the space here. So C part 1. So since the speed of sound is equal to the wavelength times the frequency, and we know lambda, and we have lambda, we will need okay, to find f, we can use an oscilloscope connected to a microphone. Okay, that's good enough, I think. You can also use a phone app, or even a phone app. There are many now that record frequencies, pretty much. Okay, so that's question I of part C. Now let's do part 2. On a humid day, the speed of sound in air increases. Explain how an increase in the speed of sound would affect the value of W for this investigation. Okay, the reason why the speed of sound increases in when the air is humid is because sound travels faster in materials. Okay, so air is not a good let's say conductor of sound, if you will. Air is not dense. I mean, it's various molecules that are not connected together, right? Whereas in liquids and even better solids, you have molecules or atoms closely packed together, so sound travels much faster. Okay, I mean, this is a physics channel, so it's good to know your physics. So, but let's go to part 2 and what they are actually asking. So since lambda is equal to V over F, okay, if V increases, lambda increases. And since W is lambda D over S, if lambda increases, the width W increases as well. So on a humid day, okay, the gaps between the loud spots increase. Okay, and to complete the kind of like candid physics discussion, in space, in vacuum, where there is no air at all, there is no sound as well, okay? So this was a question I had when I was as a small boy. I don't know, I was 7, 6, and I asked this question to someone, or it kind of bothered me for some time, and I was wondering, like, how do they communicate in space? And later I figured, okay, they have suits, and in those suits, those are pressurized suits, so they can speak, and then they speak through a microphone. But then I didn't understand how on earth would sound travel electromagnetically. And then later I learned about how you can embed a signal into electromagnetic waves and then transfer it that way. So yeah, it's been a journey, understanding things. This is why I studied physics, I think, deep down, because I was like, I'm stupid, I don't know anything. Like, how on earth do all these things around me work? It kind of bothered me. So it still does, by the way. Okay, so let's move on to the third question. Okay, question 3. A student investigated the efficiency of an electric motor using the apparatus shown. Okay, pretty much when we close the switch, okay, over here, let me use red. So if you close the switch, you see that the battery provides the motor with energy, and we have that axle there, and that okay, and then the mass is lifted. Okay, so let's read the questions. The motor was connected in a circuit including a battery and a switch. The student connected additional components to determine the power of the motor. Complete the circuit diagram in the answer book for the circuit. The student should use, I will instead use a clean page because there is not enough space there. So this is the motor. Okay, we will need a voltmeter so we know the voltage across the motor, and an ammeter to measure the current. Okay, so this is the switch they show, and we will need a power supply and close the circuit. Okay, let me fix this, it looks ugly. Okay, so that's the circuit, is part A. Okay, now we need to do part B. Let's read it. The student closed the switch in the circuit and the motor lifted the mass from the floor. She used the meter rule to measure the height gained by the mass in 10 seconds. Part I describe how she should measure a single value of the height gained as accurately as possible. You should include the use of any additional apparatus needed. Okay, so this is a 4-mark question, so we need to be detailed. Okay, so so this is B, part 1. So clamp a meter rule, okay, in a fixed vertical position next to the setup. Okay, so it doesn't move during the measurement. Okay, check the rule is truly vertical using a set square. Okay, so check the rule is truly vertical using a set square. So the set square kind of counts as the extra apparatus that they mentioned. Okay, so let's create another clean page. So attach a small marker to the mass. and place the rule as close to it as possible to avoid parallax error. Okay. When taking the reading, okay, look at the scale. The reading. Okay. Look at the scale straight on. Okay. Perpendicular to the rule. Okay. Which avoids parallax error. Okay, so that's a good enough answer. Let's go back and read the other questions. So part 2, explain why repeat measurements are appropriate for this measurement. Okay, so let's go back. So that's part 2. Single measurements have some natural variation due to reading differences or small timing differences. And by that I mean you are supposed to take it at 10 seconds. So maybe you stop the clock at 9.9 seconds or 9.99 seconds, etc. Okay, so maybe you didn't measure exactly at 10 seconds. Okay, so that's what I mean by that. Okay, so and then taking repeats, okay, and averaging, okay, reduces the effect of this random error. Okay, so that's a good enough answer. Let's finish this with part C, because there is a part C. Explain how the measurements made by the student should be used to determine the efficiency of the motor as it lifts the mass. Okay, so let me create a clean page again. So C. Okay, let's start with what the efficiency is. So the efficiency is equal to the power useful power. Actually, let me write it like this: useful P out over input P. Okay, so we need to know both the electrical power input, okay, and the mechanical power output. Okay, because I mean, if we go to the apparatus, so the input is clearly coming from the battery, right? So from the circuit, okay. So this is the input, and then the output is whatever mechanical power you produce by lifting that mass. Okay, I hope this is clear. So you can find P input by multiplying the current times the voltage using the measurements from the voltmeter and the ammeter. Okay, so that's how you can calculate P input. Now for P output, we can find that by using the potential energy, mgh, and the h is something we measure, and the mass is something we measure, divided by time, so we turn it into power. So this is the rate of doing work against gravity, where h is the height gained in time t. Okay, and then I'm gonna write it in red because it's finished here. I mean, the problem is solved, but you can also use the fact that efficiency is E useful. So you can use energies pretty much. E useful over E input, and you can use MGH for the useful. So you can use MGH, okay, for the useful energy over I times V times time. So you will need to use time to calculate the input energy, okay? So I'm gonna write it here as alternative. Okay, so this was problem 3. I hope it's clear. If it's not, let me know in the comments. By the way, guys, 95% of the people who watch my videos are not subscribed, so it's not a big deal. Please subscribe. So let's move to question number 4. Okay, question 4 is the last question in this paper. And one general thing I noticed with Unit 3 past papers and Unit 6 past papers, which is the equivalent, I mean, Unit 6 is the equivalent to Unit 3 for the A-level students. Okay, this is AS level students. This is for AS level students, excuse me. There is always a problem involving data and plotting them, okay? So there is no going around that. So practice problems where you plot things so that you do well in this exam. So 4, the activation potential difference is the minimum potential difference for photons to be emitted from a light emitting diode, LED. A student measured the activation potential difference for different LEDs. The relationship between activation potential difference and wavelength is given by the equation. E times the activation potential difference is equal to H times C over lambda, where lambda is the wavelength of the photons emitted by the LED, plus W, where W is a constant representing the work done by an electron passing through an LED, which is the photoelectric equation pretty much. Okay, so question A, explain why a graph of VA against 1 over lambda should give a straight line. Okay, let's use a clean page. So let's do this. So E times, that's a funny E. Okay, so that's 4A. So E times VA is HC over lambda plus W. Let's divide by E. So VA is HC over E times 1 over lambda plus W. So this has the form Y equals to M times X plus a constant. So the gradient is HC over E, and the y-intercept is W over E, okay? And Y is the activation potential difference, and X, the independent variable. Y is the dependent variable, excuse me, and X is 1 over lambda, okay? So this will be a straight line pretty much. It will look something like this, okay? So that's that will be VA, that will be 1 over lambda, and this point over there will be W over E, and then the gradient will be HC over E. Okay. B. The student recorded his values of activation potential difference and the manufacturer's corresponding values of wavelength. Okay, part I, complete the table in the answer book with the corresponding values of 1 over lambda. Okay, so if we divide 1 over 6.6 times 10 to the negative 7, and then that's meters to the minus 1, we will find 1.52 times 10 to the 6 meters to the minus 1. Okay, so in constructing this table, we will have 1 over lambda in units of meters to the minus 1. Actually, so in units of, 10 to the 6 meters to the minus 1. Okay, so this is the point I want to make. So here we will have 1.52, and this 10 to the 6 is common with all the other values, so we just complete the table. 1.63, 1.69, 1.71, 1.89, and 2.13. Okay, so these are our values. Okay, part 1 is done. Part 2, plot a graph of VA on the y-axis against 1 over lambda on the x-axis. Okay, so actually, let's utilize some graph paper they give us in the back. Okay, so this is the graph paper. So first of all, I'm going to write up here that the range, actually, I don't need to do that. I'm going to go back and show you actually. Let me find the table. Okay, so for VA, the range is from about 1.8 to 2.6. So in the y-axis, we will use increments of 0.1, and the same for the x-axis, because you go from 1.5 to about 2.2. So we will use increments of 0.1. Okay, so this is the point I wanted to make. Okay, it's good to think about these things before plotting. Okay, so let's draw the vertical axis. So this is VA, and that's in volts. Okay, and this 1 over lambda, and that's 10 to the 6 meters to the minus 1. Okay, so we will start from 1.8 for the y-axis, and then 1.9 to 2.1. As we said, we will use increments of 0.1, so 2.2, 2.3, 2.4, 2.5, and 2.6. Okay, and the same for the horizontal, so 1.5, 1.6, 1.7, 1.8, 1.9, 2, 2.1, and finally 2.2. Okay, it's a little bit cramped. Let's do this. So 1 over lambda in units of 10 to the 6 meters to the minus 1. Okay, so let's transfer the first point, and then I will speed up the video. So let's go back. So the first pair, actually, sorry, I have the pairs in front of me. So let's start with, we have 1.82 and 1.52. Okay, so every small square then, since we are using increments of 0.1 in the big squares, the small squares are increments of 0.01 for both V and 1 over lambda. Okay, so 1.52, 1.82 is this point there. Let me use a different color actually. So there, that's the first point. The second point, we have VA 1.97 and 1 over lambda is 1.63. So 1.63, so that's the point. And now I will speed the video. Okay, so these are all the points. We will need it, so I'm gonna draw it the line of best fit. So I'm gonna make it so it passes through the first and the last point. So yeah, something like this is good. So you have to have as many points to the right as you have to the left if they are not exactly on the curve. Here we have 1, 2, 3, sort of 4 points exactly on the graph, and then we have these points to the left and to the right. So it's good graph, I think. So let me know what you think in the comments. So let's go back and read the other questions that we need to finish in this paper. Okay, we plotted the graph, so we're done with part 2. Part 3, determine the value of the Planck constant given by the student's data. Okay, so we'll use a clean page. So this is part 3, 1, 2, 3. So the gradient is hc over E, but also the gradient is the change in VA over the change in 1 over lambda. Okay, and since we chose the extreme points, so I mean these two pairs to be on the graph, okay, we will use them to find the gradient. So 2.58 minus 1.82 over 2.13 minus 1.52 times 10 to the 6, and this is volts times meters. So this is 1.25 times 10 to the negative 6 volts times meters, which is equivalent So the units are equivalent to joules per coulomb times meters, okay? So to find H, so H, we need to multiply E, the charge of one electron, times the gradient over C, okay? So 1.6 times 10 to the negative 19 coulombs times 1.25, we need extra space. So 1.25 times 10 to the negative 6. So I'm going to put the units down here. So coulombs for the charge of the electron, joules per coulomb times meters for the gradient. And then we have to divide with the speed of light, 3 times 10 to the 8. And that's meters per second. So meters cancel, coulombs cancel. And we get the final value for H as 6.64 times 10 to the negative 34 joules times seconds, extremely close to the actual value, okay? So let's read the final question. 4, the student states that the value for the Planck constant obtained from the graph is accurate. Evaluate the student's statement. Okay, let's use another clean page, okay? So to evaluate the statement, we have to compare. So compare with H2, which is 6.63 times 10 to the negative 34 joules times seconds. So H, let's say calculated minus H2 over H2. I mean, to compare, we have to form this, this ratio. Okay, so always remember that the true value goes in the denominator, okay? And then in the numerator, we always have the difference between the actual value and the calculated value, and then you multiply by 100 to get a percentage. So 6.64 minus 6.63 times 10 to the negative 34 over 6.63 times 10 to the negative 34, this cancels, times 100, yields 0.15%. This is a tiny error, so tiny, not error, difference, okay? It's better to be precise. So tiny difference, so the value is accurate. Okay, so this this was Unit 3A from October 2025. I hope it's useful. Now there are 4 Unit 3 past papers in my channel, and I also have videos on uncertainties and such. So at some point, I might upload videos related to the experiments and the core practicals and stuff like that. But it's been tough to keep up with this channel, so give me time. Okay, hope this is useful. Please like and subscribe, share with your friends, ask them to subscribe as well, and help me grow this channel. So, and I'm hoping you are enjoying your summer. So, see you guys in the next video. Bye.